And greetings, welcome to the Evidence Reasons Academy. I'm Salvador Cordova. This is going to be another nerd torture session. We're going to be studying multivariate calculus. Glory and honor to our Lord and Savior Jesus Christ, who helps us bear our crosses each day. In doing physics, mathematical physics is a cross to bear, unless you're an ultra nerd, which would not put myself in that category, where I just look forward to doing multivariate calculus. I like it just enough to get by. This is important, preliminary to studying lots of things in the young Earth creationism question, the creation evolution controversy. Whether one is a young Earth creationist or not, perhaps one can get some blessing just expanding one's mind and horizons in scientific disciplines. This is a great opportunity for me to revisit what I had studied 30 years ago in undergrad, and then maybe 10 years ago in grad, but not so well. The teacher was so far ahead of my teaching me plasma physics and magnetohydrodynamics. I was just like, I don't remember the last 2 weeks of that class at all. Could not digest any of the magnetohydrodynamics. I'm broadcasting from in a different location in my home. I have a new computer. I'm in the middle of setting up my computer systems. So this stream is an opportunity for me to just share with my nerd friends, and also to reteach myself, reacquaint myself. Sometimes in the process, the best way to learn something is to teach it. And so when you see me kind of struggle and fumble and not do so well in my understanding, that's also a learning process for me. So the best way to learn is to teach. And so that's partly why I'm doing these streams. Hopefully some of you can get some benefit. If for nothing else, the benefit you might get is you get to see what professional scientists have to struggle to do and how much they have to suffer just to do a little bit. Maxwell's equations required the understanding of a number of multivariate operators in my electromagnetic theory book by Height. And you can see this is well worn 30 years ago. Hard to believe. This is my book 30 years ago. These are kind of the major operations. And this is so critical that they put it in the cover of the book so you can easily have access to it. So electromagnetic theory is a lot of math, and you're like, well, what does it do? This math, parts of it, you can take parts of Maxwell's equations and just do kind of your continuous steady state magnetic and electric fields, what we would call kind of static or quasi-static situations, which would apply to geomagnetism. You can also model electromagnetic waves, which explains the relationship of magnetism, electricity, and optics, which is just remarkable. It enables the construction, the production, and the receiving of radio waves, all sorts of things. We would not have a modern world without our understanding of Maxwell's equations. Just as a historical note, the equations are named after other people like Gauss and Faraday and Ampere. And why do we call it Maxwell's equations? He was the one that unified the relationship together in a set. Definitely you can do a lot of electromagnetism without the full set. You can just take pieces of it, and many times that's desirable because the whole set is kind of hard, kind of unwieldy. So what was the thumbnail about? Okay, when I Google the word curl, we're going to study the curl operator. And let me just see something here. Curl. All right, this is going to be funny, sort of. At least I'm trying to be funny. When I Google the word curl, this is what I get. Greetings, Schnoil. Nice to see you. So this is what's funny. I type in the word curl and you get this. And so I said, okay. So, you know, I get a picture like this, a girl wearing curlers. And a friend of mine, she was saying, oh, I have to go get my hair curled today or straightened. I don't remember which. I said, Kim, I mean, some girls go through a lot of trouble to get their hair curled and you're trying to straighten yours out. Or it was, I don't even remember. It was one or the other. She said, oh, it's a girl thing. I'm like, okay. So definitely some women like to have their hair curled. I kind of like not excessive curling, just a little bit of a wave. That wavy look is beautiful. Otherwise, straight is fine. That's just my personal taste. What's important is the quality of the hair, that it be smooth, that indicates youth. And as we grow older, the hair becomes coarser. Anyway, neither here nor there. My mother was a dressmaker and a cosmetologist. So it's a girl. So I don't know. I just having a very curious mind, you know, I began to learn a little bit of some of the stuff in cosmetology. Not that I was that much into it. But, you know, that was our household. It's, you know, like my mom would like to watch love stories. And so when she needed some company, I would watch those love stories with her. Dad loved war stories, and I really love war stories. So we would watch movies together. So it was really funny. Depending on what movie was playing, it'd be a different parent I'd spend time with. So anyway, so to get the right Google search term, let me see. Let me go back to where we were. If I type instead of curl, let's see what we get when I type in curl operator. There you go. All the difference just a word makes, huh? So that led to my thumbnail, which, let me see. Sorry, I need to get my, I'm having a little problem with my mouse pointer. Let me get rid of this. So that led to this thumbnail here that I call the girl curl or the curl girl, whatever. So I just combined the two. So that is the curl operator in spherical coordinates, and it's just miserable. It's a mathematical operation where one uses lots of first order partial derivatives, and it can be expressed in the matrix. So the reason I'm specifically covering curls today is that in about 3 hours, I'm sorry, Schnoil has just some great comments here. Yes, the math is way more beautiful than the girl with the curls. So in about 3 hours, Russell Humphreys will be on the show. And as I was reviewing, I'm going to have a review of his paper, and there's curls galore in his paper. And I just needed to review it. And so we're just going to go through some of the math, and just enough to get reacquainted with it. To do this in more depth, one would have to. It's good to do some exercises just for the practice. So it's really more of an accounting thing, and being able to like kind of put kind of the right components in the right shelves, so to speak. So if you can kind of do the operation that way, then you can get it right. The problem is you have to do it 100% accurate. Otherwise, just a little, I mean, you guys know, you've done math. You could have this monstrous equation, and if you happen to just flip the sign of a plus to a minus, it just leads to disaster. And then you have to go back and redo everything. And so these equations get bigger and bigger and bigger. And I did mention in passing, I'm doing some stuff with Laplacians, which was the prior topic in part 2. I'm excited to say I found, let me see. I was trying to do a proof that related Maxwell's equations to special relativity. So let me just, I'm going to get the curls, but I just want to, I was just so excited because I was just agonizing. I'd done this proof in graduate school. It was my first day in graduate school at Johns Hopkins. The professor said, I want you to show the Lorentz invariance of Einstein's equations. And I was like, fat chance. But he kind of coached us, and he said, well, okay, guys, you know, I'm gonna just help you get the proof going, and I'll give you some pointers. So we started with this. This is the electromagnetic equation, wave equation. And there's the Lorentz transforms, and then all of the derivatives. And I was working through this. So we were able to demonstrate that time, or dare I say clocks, change the faster you go. It was experimentally demonstrated with these, the Half-L-Keating experiment with cesium beam atomic clocks they rode on an airplane, which is really cool. Got to travel doing an experiment. Hey, life for a physicist doesn't get much better than that. So then I was going through this equation, and then I started applying the Laplacians. So this is the Laplacian operator right here. And when you do the Laplacian and you transform the coordinates, hopefully you end up with kind of the same form. And I was just doing all these Laplacians. And then this is using the chain rule with the Laplacian. It gets really nasty. And it just got monstrously big. I mean, I was just getting cross-eyed looking at all these symbols. I mean, this is not, you know, it can be done, but it's kind of like, you know, really literally chiseling away at a sculpture. It's just very slow, tedious work. In fact, one reason I tried to use Wolfram Alpha for some stuff. Wolfram Alpha doesn't really do kind of these kind of more abstract proofs. Or at least I haven't been able to figure out how to use it to be able to build something like that. I'm sure there are people who've been able to do mathematical proofs with computers, but some of the insights are best done, I think, kind of with human calculations. The other thing is if it starts to get too ugly and complicated, maybe it's not a theory worth pursuing. I'm just pointing that out. This kind of as a principle, what they call elegance and simplicity is very important to physicists because, I mean, if you look at the major laws of physics, like say F equals ma, it's very simple and elegant, but it describes a large variety of phenomenon. And then also E equals mc squared. Schrodinger's equation is kind of a little gnarly, but it's only a second order differential equation with partial differential equation. It's not horrible as, you know, the potential for horrible to get. And so just going back, and then we'll get to the curls. So these are the consequences of Lorentz transformation. And I had done the first round of differentiations, partial differentiations, and I got a simplification here. Even then, that simplification was just a lot of terms, 1, 2, 3, 4 terms, and then some stuff inside. And it's all symbolic. And I was getting all cross-eyed doing this. And I had to skip some steps, and then I could simplify the proof. And I finally, I mean, this was just miserable. I simplified it. I had to skip a step, and then I was able to prove Maxwell's equations lead to special relativity. Now, I shouldn't say I was able to do. This was a homework assignment every student was given the first day of graduate school. And all of the homework problems were reasonable. This one took me about 4 hours to get through. The main reason I got through it was I had help from the professor gave some pointers how to just grind through the math. And at first I was just like, this is too daunting. But then it kind of just fell through. If you're just, if you can add two numbers together, it's kind of the same. You can add 3 and, then you can add like 50. It's just more to work with. So a lot of this was just kind of, because he gave the point, I wouldn't have been able to solve this if he didn't give the pointers. The problem was I'd lost that homework assignment from way back in 2007. And there was a key part of being able to state one particular second order derivative, and I didn't know how to do it. The link, I prayed to God and I searched for like an hour. I said, it's in vain. I don't think I'm going to find how to do that derivation. In the video description, I found it. Dr. Bursha, who teaches electrodynamics and relativity, I think also in one class, she gave the proof. When she walked through this proof here that related Maxwell's equations to special relativity, it took her 30 minutes, and she was just writing it out, and her handwriting's just awful. I mean, it's bad enough trying to read. It's bad enough trying to read these symbols when you've got really nice fonts, and then on top of that, her handwriting was awful. I couldn't tell the difference between 2 and a partial, or V and a U. And then like she had these gamma symbols. I'm just like, please. But I kind of recognized the pieces of what she was doing. And she was kind of clever. She found some ways to decompose the problem. And I'm excited to say, I'm going to recapitulate it. I'm going to have it in nice text, and I'm going to publish it in an educational article for the Blythe Institute, and then just add a little bit of considerations for special relativity, and also why I think there's an absolute reference frame. I will make that argument, and I think I can defend it. I'm going to clear it with people like Philip Dennis, who is a young Earth creationist, but also an excellent secular scientist who consulted with NASA on special and general relativity. He consulted for NASA. NASA has to, like, for example, adjust the adjust the space probes for effects of special and general relativity if they have clocks in them. I knew the professor who gave me this proof to as a homework assignment. He was saying they were having, they had to account for their space probes to have very precise clocks. They had to account for the effects of gravitational field and also velocity in order to get the clocks properly synchronized for the space probes. So I found that really fascinating. So this is, if people wonder why we go through such agony of math, it's to build things like GPS and also have very precise clocks. So that being said, we can now move on to the topic of the show, which is curls. Curls. So we're going to do curls. So let me see. I have to find the paper. Give me one moment. So the paper I was looking for, I hope I have it here somewhere. I hope I didn't lose it. I had it here just a moment ago. Apologies, gentlemen. One moment. I had it here just a moment. Okay, I know. I had it in my folder. It's called vector calculus. All right, now we're in business. I think I found it. Oh my, dropping in to boot statistics. Oh, thank you for giving me some views, Emery. Since you dropped in, this is in preparation of me meeting Russell Humphreys this afternoon at 3 p.m. to talk about geomagnetism and why the Earth is young, which helps us to know why the Gospels can be trusted. So this is a big cross to bear to get through this, but God bless you. It's just great seeing you. So these are vector operators that we need to understand Russell Humphreys' work, because we need this to understand electromagnetic theory. We covered the gradient of a scalar field in a prior part 1, and we also covered the divergence, part 1 and 2, divergence of a vector field that computes a scalar. So gradient is you operate on a scalar field, you get a vector. A divergence is you do an operation on a vector field and you get a scalar field. And the presentation on Laplacians, we just talked about it, was a little bit confusing because you take the this divergence of a gradient of a scalar field. So you generate a vector field using the gradient, and then you take the divergence of that and you get a scalar. The difference is from this presentation and the way it's done in electromagnetic theory is you actually use a scalar. There are scalar Laplacians and then vector Laplacians. This is a scalar Laplacian, but you actually apply a scalar Laplacian to a vector field. it's just very specialized, and that's kind of peculiar. We'll cover that maybe in part 4. So now let's get to the curl of a vector field. Let me see if I can just illustrate what a curl tries to do, mathematically speaking. So in the meantime, while I look this up, here, this is a different way of looking at the curl. But let's see here. I'm going to look for a diagram that illustrates what the curl operator will do. So one moment, I think I have some visuals. Just give me one moment. I think I have some nice visuals to help illustrate. All right. So if we have a vector field, and this would really apply to a magnetic field, I'm pretty sure this would apply to a magnetic field. At a point, we want to see the tendency for the field to curl around that point or turn, the twist or turn. And so the curl will give a kind of the intensity of that turning. Now, unfortunately, let me see if I could show this. I'll try to illustrate this with a pen. So if you have a point in space, you can then do the curl operator, and then you get another vector. It's just a conceptual vector. And it'll orient the vector in terms of how the curl is, how it's curling in space. So if there's a curl, it's going to curl around like that, around that vector. So you try to create a vector where the axis of rotation around that point is rotating around the vector. So this pen is like a vector. The vector gets bigger as there's more curl and smaller as there's less. I hope that's right. Anyone out there, if I'm wrong, tell me. So you just get this whole set of vectors, and you're just like, what's this about? Well, you're trying to find how it is turning. Now it's really obvious in 2 dimensions that it's just curling about that point, and you can have the vector kind of what we call normal, perpendicular to the plane, to the 2-dimensional plane. And unfortunately, okay, so we have it kind of a 2-dimensional plane, and then you have a vector pointing out like that. So just imagine that I have a pen or a vector pointing out from that 2-dimensional plane over there. It's too bad I can't actually, I can't. If I could use this as a background, I could actually show how I'm pointing out. So just might have to imagine that. Let me see. There's another picture. I have another picture here. And so you could see the curls. You could see the curling here. So at this point, you have probably a curl of some magnitude, and then a curl here, curl there, a curl there. And then in some places, you don't really have much of a curl. It's just kind of straight. And so your vector magnitude will be 0. I mean, it would be worth making a visual animation to kind of illustrate the concept. You know, it would work nicely in 2 dimensions. In 3, it's going to be nightmarish. And unfortunately, we have to do curls in 3 dimensions. So anyway, I'm just trying to describe kind of qualitatively, when you go through all these operations, what do you make? You're making a vector that will point. You're basically making a vector. If you illustrate the vector as like this pen, you're giving it length and then also its orientation in 3D space. All right, so that's what the curl will do. And there's going to be lots of curls in Dr. Humphrey's paper. So that's about, I'll probably figure a way to better explain that. So let's go back to our vector calculus paper. And I get kind of, let's see. Let me stop this a while. Every time it seems when I do a Google, it just kills. It kills my window. All right, so hang on. I have to install Adobe Acrobat. Maybe this will make it better. Apologies. So like I said, this one reason we teach is so we can learn. And that's one reason I'm teaching, and I'm just fumbling through this and I'm learning the hard way, even how to operate basic things. Gradients, divergence, Laplacians. Now we get to the curl. All right, I'm just going to read through this. Let's suffer through this together. So far, we've seen the operator del applied to a scalar field, delta u, and the dotted with a vector field, del dot a. So that's the gradient, then divergence. Now we are overwhelmed by an irresistible temptation to cross it with a vector field. So we can multiply it, we can dot it, and then now cross it. So let's do, this gives us the curl of a vector field. We are now overwhelmed by an irresistible temptation to cross it with a vector field. I mean, I wonder, did mathematicians just say, let's just try to do this operation and see what we get? I mean, is this where it came from? It's like, did you have nothing better to do? Let's just see if we can, all the torturous ways we could just manipulate symbols and create rules to how to manipulate it. It's just like, did you just come up with this? It's kind of funny. That'd be interesting how the history of how they concocted these operations. We are now overwhelmed by an irresistible temptation to cross it with a vector field, del cross A. This gives us the curl of the vector field. So del cross A is curl A. So now in terms of calculus operations, we're just going to kind of just elaborate. So we can follow the pseudo-determinant recipe for vector products so that del cross A, you have a 3x3 matrix where you have the identity vectors I, j, k. In some texts, it would be x hat, y hat, z hat. And then you have these partials, and then you have ax, ay. These are the coefficients to your vector equation. And then you get this in Cartesian coordinates. Now, it can look really nasty when you put this in spherical coordinates. So this is also a curl here, but this is in spherical coordinates, and you get a really nasty looking equation here. Or well, no. I like the way this beautiful equation, because just to quote Snow, the math is way more beautiful than the girl. Curl math is more beautiful than this girl. Okay, so going back to the curl, I don't know why I can't. Okay. I know why I was having some problems. I have Chrome and Microsoft Edge doing this to me. I'm going to try. This is a new computer and it's just behaving not the way I'm used to. I have to reconfigure it. So this is curl. This is the curl in Cartesian coordinates. This is the curl in spherical coordinates. Ideally, one wants to hopefully get a curl that is not too bad. You choose your coordinate system so you can kind of get rid of some of the terms, like you want to zero out the I, J, K or whatever. I mean the I or like the J and the K. So in the example of spherical coordinates, many times you might luck out and you can get rid of some of, like a term like this. That's why one would choose a particular coordinate system so you have fewer things to deal with. I mean, it's nice if you can just zero this out and then zero this out. All you have to do is deal with this. So going back, perhaps, okay, this is a nice teaching tool. Perhaps the significance of curl. Perhaps the first example gives a clue. The field A equals minus y I hat times x j hat is sketched in figure 5.5. So this is a vector field. So this is kind of like vectorially what this would look like in 2 dimensions. Mercifully, it's 2 dimensions, not 3. This is a good visual. So you take this, and this is the vector field. This is kind of a visual representation of the vector field. It's a field you would calculate as the velocity of an object rotating with omega equals 0.001. Okay, so it's rotating around here around the origin of the xy axis. I think that's how I interpret it. This field has a curl of 2k, which is the RH screw sense out of the page. You can also see that a field like this must give a finite value to the line integral around the complete loop. I got an important call. If you could just hang on a minute, maybe I could postpone it. I had to take that call, guys. I almost never interrupt streams. You could tell this was really important. So it just mercifully, I'm almost about done. So again, see if I need a prop or something. So what they're illustrating is you have kind of that vector field where the vectors are obviously circulating, like say a tornado, and the tornado. So if you have a tornado moving around here, the size of this abstract vector is pointing out like that. That's what he's describing. And the length of the vector is the strength of the turning. If there's no turning, the length of the vector is 0. So let's go back to, oops. Let's go back to what this is saying here. The field has a curl of 2 k hat. All right, let me just explain. So this is the y-axis. Wait, this is the x-axis going like that. And it's defined by the I unit vector. Like that, I corresponding to x, y corresponding to j. Okay, I corresponding to x, y corresponding to j, and then z corresponding to the k vector, like that, in and out, okay? So I like x hat, y hat, z hat. They like ijk. It depends on the text you're using. So let's wrap this. It says you can also see that a field like this might give a finite value to the line integral around the complete loop. So we do a line integral a dot dr. They didn't have to say that. That just added a confusion factor. I mean, that has relevance to electromagnetic theory, but dot dr, a dot dr. A dot dr. I'm gonna have, I mean, that has some meaning. I think, I mean, that looks like 0 to me, but we'll see. Anyway, I could be wrong about that 0. Just get rid of that idea. Sorry. A rough sketch of the vector field y I hat times x j hat. In fact, the curl is closely related to the line integral around a loop. The circulation of a vector A around any closed loop curve is defined as A dot dr, and the curl of the vector A represents the vorticity or the circulation per unit area of the field. Oops, I think I just misstated something. So I wonder if what they're saying is A dot dr. I wonder if the magnitude of the vector created by the curl is equal to that line integral. Oh boy, line integrals. Okay. So the circulation of a vector A around any closed curve C is defined to be the line integral that circulates A dot dr, and the curl of the vector field represents the vorticity or circulation per unit area of the field. I got to tell you, to try to execute a line integral here, you'd have to use some sort of trigonometric, going from 0 to 2 pi, and you integrate from 0 to 2 pi, which we've done in second semester calculus, but just setting it up to do that line integral. Our proof uses the small rectangular element dx dy shown in figure 5.6. Consider the circulation around the perimeter of a rectangular element. So instead of a circle, we'll do a square. The fields in the x direction at the bottom and the top are equation 539. What the heck does this mean? I freaking don't know what this, how do I interpret that? Good gravy. I've never seen anything like that. Okay. I can do this. This means we take if this is the vector xyz, no, this is, all right, let's go back up to this diagram. We have xyz point somewhere here, and then we would take the derivative, the ax component, which would be here. I'm going to have to work through this. I kind of know it in my head, but it's hard to kind of do this on the fly what these symbols mean. So ax is this coefficient here. Ay is this coefficient here. Yeah, like that. Okay, this may seem confusing. This is good to visualize what this equation means, by the way. So the farther you go out here, the bigger you get this vector, which points in the y direction. So the larger the x, the larger the vector in the y direction. So x here, as x gets bigger, you get this bigger vector. All right. So now, and then likewise for the y for this. The higher the y, the bigger the vector in the x direction. Schnoil says, the math is one thing, understanding what describes is a different thing. Oh yeah, absolutely. Remember I said I cheated, not academically, but kind of like in the sense I could do the math operation. And the math was so powerful and so precise, you could do the derivation without knowing what it described. And so in an examination, when the professor is asking you exam questions, he's not going to try to ask you to describe what the math is describing, because you could see how difficult this is to describe intellectually. And if I were teaching it, it would not really be a fair exam question to say, what does this describe physically? It helps if you understand what it describes physically, but you can actually get through the course just being able to do these rote calculations. I mean, what will happen typically on an exam, depending on how merciful the professor is he'll actually give you in the exam the equation for a curl operator. And then he'll give you the vector field. So like you might get a description of the vector field described by an equation like this. So you get an equation like that, and then he'll give you on the exam also the curl operator, and you just grind through it. Now you probably wouldn't use a spherical version like that. You'd probably use of the curl operator, you would use this kind of curl. So you would get this. Many times you're just given he'll give you the cheat sheet. You know, he'll give all the students, he'll print out a cheat sheet. When I took electromagnetic theory, the professor handed out the cheat sheet. And Lord help you if it's an open book exam, because it's going to be brutal. You know, the questions are just going to be nasty on an open book exam. But sometimes to standardize what each student is working from in terms of open book, you'll get this on your exam, and then he'll say and this is fair. He'll say now, apply the curl to this. I mean, this is just really basic. And so it's like, well, I don't know what the heck this describes, but I can do the operation. And sometimes that's where you really have to begin. So the great point, Schnoil. The math is one thing, understanding what describes is a different thing. So if I were teaching this, I would actually just try to, you'd have to do a mix of conceptual and then, just purely math, what they call plug and chug. So like I said, that's how I got through a lot of school. I'm just like, I got through the class. Many times I get an A, but I'm just like, physically, what is this describing? And I think that's the thing, unfortunately, when one is in school and one is just trying to make the grade and you're pressed for time, it's like, okay, I'd like to have a chance to actually understand what the math is describing, but I got to get the grade. So you tend to focus on being able to do the derivations, and sometimes what's lost is what it is kind of conceptually describing. And so I focused a little more on the conceptual description. Now, unfortunately, as I'm walking through this here, I'm trying to understand what you see, this A, X, Y, Z. I'm trying to relate it to what A, X, Y, Z would be here. So there's a lot of time just trying to understand what the symbols mean. So A, X, Y, A, X, X, Y, Z, I think would be, in this case, this coefficient here. And I'd actually have to do that. And then and then you have this partial AY, AX. Partial AY, AX. All right, well, let's just see where this goes. Starting at the bottom and working around in anti-clockwise sense, the four contributions to the circulation DC are therefore as follows, with the minus signs take the account of the path being opposed to the field. Okay, I'm not going to go through this in detail. This is just, ugh. Okay, NB. NB, I think, means not bolded. Or I don't know. Again, this is not a completely rigorous proof, as we have not shown that the result is independent of the coordinate system used. And I freaking don't know. Okay, he's trying to prove the circulation. Okay, here it is. Del cross A dot ds. Del cross A dot ds. Okay, so this is the vector We generate a curl, that's one vector, and then we dot it with the S vector. This is not the best here, guys. I'm sorry to say. This is very terse, and this is like, okay. To do this part is nasty. I can see it already in proving it. This DS thing is a little funny. Let me go back up here. See, he uses this thing called DR, and I think in another situation that's DS. No, I'm sorry. This is not making, this was an otherwise good document up until he got to this point. All right. At least now I know not to go there. So as far as for today, in 3 hours, Russell, 2.5 hours, Russell Humphreys will be here. All that is really needed to know is the curl operator is just using first order partial derivatives, and you just have to plug and chug. You can use, this is the curl operator in spherical coordinates, and this is the curl operator in Cartesian coordinates. It just ends up being just tedious. It can be done, and that's about all that we need for the curl. Yeah, yes, and good morning. So with that, I have to call my, I have to take the call. I have to follow up, get back to that person I had to postpone, and we'll resume in another stream that'll run a little late. And we will be talking about, we'll be doing readings of Russell Humphreys' paper. And then at 3 p.m., the author, Russell Humphreys, will be joining us. So glory and honor to our Lord and Savior and helping us bear this cross. Thank you all for forbearing with all the fumbling and difficulty. That's just the way things go with this. It's kind of, it's never smooth. Electromagnetic theory is notoriously one of the toughest subjects. So take care. The Lord Jesus Christ richly bless you.